And so the question, what should I use? The answer is that it depends on the problem. For instance, if you have good reason to believe the data partitions into independent groups, then you can use graph clustering like we did with the subeconomy problem. If there's only a few features and you have some intuition about how important those features are, you can use decision trees. If rewiring is possible and there either are only a few features or the data is sparse, then k-nearest neighbors. And if it's linearly separable, then logistic regression, which we tend to think of as the workhorse of predictive modeling. But what if I have a data set that is not linearly separable, does not have interdependent hubs, some small world structure, is not sparse, and does have large numbers of features? In other words, what if I've got a data set like most of the data that people are calling big data, and most of the data that is relevant today that people would like to see analyzed because it makes nice predictions? Well, here in 2 slides is the hierarchy. First off, you'll want to use multiple runs with many training testing set partitions. We've done, for academic reasons, only a few, but if you were doing this for a job or for research or something like that, where you're not trying to get everything done in an hour or 15 minutes, then you might test for an entire week. So you might generate 100,000 cross-validations, something like that. But this testing is extremely important. After you understand the importance of testing, then you'll know that you can start with logistic regression. If it separates the data, then you're done. In other words, you're going to evaluate it with metrics and see what the metrics tell you, and that will tell you whether or not logistic regression was a good approach. If not, then it may be that the data is linearly separable in higher dimensions. So next, try using support vector machines. These are just linear classifiers like logistic regression, but they're applied after the data is embedded in a very high dimensional vector space. In fact, the embedding space may be infinite dimensional, what we call a Hilbert space. So again, remember, use multiple runs, lots of training, lots of testing, and lots of metrics, lots of evaluation of your results. If the support vector machines don't work, then you can always turn to the universality of artificial neural networks. The nice thing about artificial neural networks is they will work, but they may aid you significantly in the process. An alternative is ensemble methods, which have somewhat the sense of the universality of artificial neural networks, but are not truly universal. But in those methods, you're bootstrap sampling over many different approaches, and example there is random forest. So on the final exam, we're going to be doing this hierarchy. We're going to be looking at various data sets. So we're going to look at leukemia, microarray data, 72 observations of 7,129 features, or genes. And these are microarrays, which means for a given subject, we measure the activity level of each gene. So essentially, you take a biopsy, you do a genetic profile of the biopsy, you look at how each of the 7,129 genes, how much activation there is. And you do this for 2 classes, a class with leukemia and a class that does not have leukemia. And the goal is to predict an unlabeled observation. But there's also another goal, and that's feature detection. In other words, once you have a good classifier, then you can ask the question, which genes were most important in training this classifier? And that might tell you which genes are most relevant to causing leukemia. Now, there's some pre-processing that's been done already. Each collection of gene activities was normalized to a mean of 0 and a variance of 1. This is called standardization. And the range, the normalized data ranges from approximately -8 to +8. So remember, a mean of 0 and a variance of 1 simply means that anything from -2 to 2 is probably to be expected, a couple of standard deviations away. But there will be occasions where you can get -8 to 8 standard deviations away from the mean. There's also going to be a final exam data set involving digits. And here we'll be modeling with neural networks. Actually, I think I've changed that to support vector machines, which converge a little faster. So the idea here is we've got lots of data where people drew the numbers 0 through 9 and on 32 by 32 grids, and then we took those images and converted them to matrices, and we reduced the dimensionality of the problem by a sampling method. And this approach generalizes to lots of applications, handwriting recognition, for example, many of those. We'll also be looking at some heart disease data. This is a very tough data set to work with. What it is it's originally 75 features that are medical tests and physiological parameters, age, sex, height, weight, so on and so forth, and then results of tests like treadmill tests and so on and so forth. And the idea is to try to predict whether or not somebody has heart disease or not, primarily as a way of determining which of these features are most important. In particular, how important is cholesterol? How important is chest pain to be an indicator of heart disease? And so we'll be working with that. We'll also revisit the iris data. Remember, the logistic regression can't separate the iris data. It's not linearly separable. And so we'll look at, well, what can we do? And maybe logistic regression is the best we can do. But we can't know that because we can't make an assumption of linear separable with the iris data. And we'll look at one other problem. And we're only going to look at one, the Mod 2 version of the generalized XOR problem. And this is strictly a mathematical problem that we use to study machine learning, how effective a classifier is, how effective an algorithm is. Now let me just finish up by saying that we used throughout the entire semester an object-oriented approach. We didn't use R. I like R. We use R for lots of things. But R is not strictly object-oriented. It is if you get something called bioconductor, then you can use S4 and S5 classes. But there's a huge advantage to using object-oriented, in particular for us, Python, for predictive modeling. So of all the algorithms we've looked at, we've barely scratched the surface of what's out there. There are huge numbers, and huge numbers coming out nearly daily, probably 4 or 5 papers a week that I'm aware of that are introducing new methods in predictive modeling. The nice thing is that when these are embedded into an object-oriented approach, new algorithms work pretty much like the old algorithms. In other words, people create a classifier object, and all classifier objects are essentially classifier objects. So if you learn how to use one classifier object, then you can pretty much use them all. And what we say is that object-oriented programming has a small second learning curve. In other words, once you've climbed the first learning curve and figured out how to do things, there isn't really much of a learning curve in the future. Unlike other software tools where you learn to use a special tool, and then when you switch to something else, it's an entirely different experience. You have to figure out how to use that and what's different about that. Object-oriented gets around that. Also, objects can store both data and methods. And this is very important because there are good reasons, beyond the scope of this course, but there are good reasons to not separate the data from the methods. In other words, when you send data to a processor, send the program as part of the data, so the processor is getting the program and the data from the same place. So, what that means for us on the final exam, as you're about to see, is we've done sklearn, the scikit-learn. We've looked at some decision trees. You've seen logistic used in videos. But the thing is, once you know how to use one such approach, pretty much with small variations, the other approaches are all going to work pretty much the same way. So in summary, this course provided an experience. It was admittedly a minimal experience. I didn't want to try to do something beyond our prerequisites of calculus and linear algebra. And in particular, I was trying to mainly just stick with calculus as the prerequisite. Because this is nice stuff, and you should be able to learn, even at the graduate level, very advanced ideas, at least in a minimal sense, without having to have so darn much background that you practically are a PhD before you can even have the conversation. So this course provided a minimal experience, minimal because I didn't want to require all the math that would be required for a full experience. And I also wanted to use only enough computer background for minimal. So in some sense, the ideal would have been if you had courses in functional analysis and real analysis, courses in MathStat 1, MathStat 2, Statistical Methods 1, Statistical Methods 2, numerical linear algebra. Definitely would need some measure theory. Definitely would need differential equations, even some nonlinear partial differential equations, and a course on Fourier series and Fourier analysis. And you would need 2 object-oriented programming languages. And that would have been the ideal, but the only people that could take that kind of course would probably be PhD candidates or postdocs. So, in some sense, I've only given you a minimal experience, but I did so in such a way, hopefully, that everything currently at least builds on the same set of ideas that this course emphasizes: pre-processing, algorithms, the use of metrics, validation, testing. So even the most advanced ideas like Boltzmann machines and deep learning algorithms, even those ideas map back to this basic structure that we've now got some background in. So what does that mean? That means that you go out of this course ready to start anything, or maybe get employed working with stuff. As people who've taken this course in the past, there are many students who took this in the past who are working for companies as data scientists. There's a lot more to be learned, but hopefully you're at the point where you could start something and then learn on the go by building on this background that you've gotten through this course.